So welcome to the 10th problem solving session for structural analysis course. In the past few weeks, we have been looking at various methods of analysis of statically indeterminate structures. So today we'll be looking at a displacement method of analysis, which is the moment distribution method. So this is basically an iterative method. It's an iterative method. And it does not involve solution of simultaneous linear equations. If you recall, in the force method, what did we have? We had a matrix F11, F12, F21, F22, and so on. We had what is called the flexibility matrix multiplied by the unknowns, which are the redundant forces. Equal to the prescribed displacements at the nodes. D2L and so on. So in this case, we had a linear system of size ns cross ns. We had ns number of unknowns, and we have to solve for them. And what did we have in the slope deflection method? So in the slope deflection method, we had what is called the stiffness matrix. Let us call it K11, K12, K21, K22, and so on. We had the rotation at intermediate joint. The joint rotations were the unknowns, say theta A, theta B, and also the support settlements, delta A, delta B, and so on, is equal to what? Is equal to the prescribed moments and forces at every node. So we had some forces, F1, F2, or moments. So what was the size of the system? If the degree of kinematic indeterminacy is nk, this had an nk cross nk simultaneous linear system. So how this method? So these involve the solution of linear equations, but in the moment distribution method, we don't have it. So this moment distribution method was developed by Hardy Cross in the 20th century. So before advanced computing systems were available for solving simultaneous linear systems, this iterative solution was a powerful addition to the field of structural analysis. So let's quickly look at an overview of the method. So as with any other displacement-based method, the moments are, the sign convention is as follows. Moments are positive when they are clockwise. Rotations are positive when they are clockwise. And if it is anti-clockwise, they are negative. For this method, the key idea is, what is the key idea? So key idea is, it is a method of successive approximations. So we do successive approximations. So what do we approximate? So given a multispan beam, multispan continuous beam, statically and kinematically indeterminate to a very high degree, we know that these joints, suppose they are subjected to some loading, we know that these joints are going to rotate by some angle theta. So this joint is going to rotate by some theta. This is also going to rotate by some theta. For a moment in this method, we'll assume that the joints are locked from rotating freely. So we are virtually locking the joint from rotating. Lock the joint rotation. So once you lock the joint from rotating, what will be the moments that are generated? That will be nothing but the fixed end moments. Okay, so if we have, once we lock the joints, so suppose I don't allow this rotation, whatever is happening here, if I don't allow the rotation, then the beam that I have will be something like this. Here also it is fixed. Here also it is fixed. Now, corresponding to these loads, there will be certain moments that are generated, but those are very easily known from our table of fixed end moments. So once we log the joint rotation, then what will be generated? Fixed end moments will be generated. But are those fixed end moments statically admissible? So whatever solution we are getting is kinematically admissible because we are just taking one theta, one variable theta. So and which means the theta to the left hand side of the joint and the right hand side of the joint is equal. So the displacement field is compatible. But what about the equilibrium? Because we are artificially restraining the joint from rotating, and then we are finding the moments that are generated. But if you see, if you take a joint here, see, let us call this as A, B, C, D. If you take the joint P, there will be a certain rotation which is MBA. There will be no rotation, and there will be a certain moment that is generated due to this applied loading. Let us call it MBA fixed end. Similarly, because of this applied loading, there will be another moment that is generated, which is MBC fixed end moment. If the joint is in equilibrium, what do we expect? We expect MPCF plus MBAF should be equal to 0. So this is an equilibrium condition. But that will happen in the real beam. When the joints are allowed to rotate, the joint generates such a rotation so that it develops enough moment to counteract the imbalance that is occurring from the fixed end moments. So once we lock the joint rotation, there will be fixed end moments that are generated, but the fixed end moments on both sides of the joint need not be necessarily the same, because that is not the correct solution to this problem. So there will be an imbalance. There will be an imbalance in moments. Imbalance in moments at the joints. What do we do to the imbalance? Distribute it. So we distribute this imbalance. So you distribute. So you once you have locked it, it generates some fixed end moment which are unbalanced. Then you allow the joint to rotate. You keep the loads fixed. You don't perturb anything else. You allow the joint to rotate under the moment imbalance itself. So suppose there is a moment imbalance of 50 kilonewton meter, right? Just for instance, if you find out MBCF plus MBAF is not equal to 0 and it is equal to 50 kilonewtons meter, what do? We already have computed the effect of the fixed end, the applied loading as the fixed end moments. Now to these joints, you apply a loading of minus 50 kilonewton meter. Right? So when we apply this incremental moment, which is counteracting the moment imbalance, then it will satisfy equilibrium at the joint. But then what will happen? Once you apply this joint is going to rotate, and that rotation will cause additional moments at the other joints. So once you have distributed the moments in proportion, so in proportion to, we'll see in detail, so in proportion to the stiffness, the next step is to carry over the moment to the fixed supports. So we keep doing this iteratively until the moment imbalance becomes very small. Do this iteratively until the moments are balanced. So this is the key idea, right? It's a method of successive approximations. You don't deal with any simultaneous linear systems. How does the method work? We assume that under the applied loading, the joints are all fixed. They are not allowed to rotate. By that, they will generate certain fixed end moments, but those fixed end moments will not be in equilibrium with each other. So what do? We'll find out the imbalance, find out how much moment we should apply to counter the imbalance. But if we apply so much moment, what will happen? The joint will rotate. As the joint rotates, it will distribute the moment to the other joints as well. So this is the key idea of this method. Now, before we get to the problems for today, is there any doubt with this? Any doubt? Okay, fine, no problem. I'll go ahead. So once we have, so what is that we need to find out now? So we need to find out what we need to find out here is the joint stiffness. So suppose we had just one beam at a joint with the far end fixed. And if we apply a moment m, it rotates by some angle theta, call this angle theta. And how are these two related? We know they are related by the slope deflection equation. How is that? So MAB is equal to 4 EI by L theta A. So theta is nothing but theta plus 2 EI by L theta B. But if the far end is fixed, theta B is 0 and there is no support sinking or anything. So it is just 4 EI by L theta. Now suppose we had multiple members connecting to a joint. The joint rotates only by theta. That is compatibility, right? So suppose if the joint rotates by theta, so let me call it O, A, B, and C. Suppose the joint rotates by theta under an action of a moment m. So what happens? So these beams will deflect in this way. And as they deflect, we have theta OA is equal to theta OB is equal to theta OC is equal to theta. This is the compatibility condition. The joint is rigid. So the 90-degree or whatever angle is initially in between the connected beams is preserved as the beam deforms, which means all of them rotate by the same angle, theta. But what are the moments that are generated? We get MOA is equal to some 4 EI by L theta. MOB is equal to 4 EI by, let us call it OA, LOB theta, and MOC is equal to 4 EI by L, LOC theta. So these all moments act at the same point, so we can sum them up as M is equal to MOA plus MOB plus MOC. Now these coefficients of theta, I can call them as KOA, KOB, and KOC. Why is that so? Because they relate a force-like quantity M to a displacement-like quantity theta. So it's like F is equal to Kx, we have M is equal to some torsional spring times theta. So this is nothing but KOA plus KOB plus KOC theta. So this is the total stiffness of the joint to rotate by an angle theta. So this is the moment rotation relationship for the joint O. So suppose there are so let's formalize it. If far end is fixed, we have already seen the stiffness of a member with far end fixed is nothing but 4 EI by Li, 4 EI by Li. That's it. So multiply by theta, you get the moment. So this is the stiffness of a beam at a given point when the far end is fixed. So this comes from the slope deflection equation. And what is the stiffness of a joint? The joint stiffness, it is nothing but it is just the sum of all the stiffness of beams. So if there are n number of beams connecting at a joint, then the joint stiffness K, the joint is nothing but summation of all the beams connecting at the joint. That is simple. Now, once we know this, what do we do? So we define what are called the distribution factors. That is, if we apply a moment M to the joint, by apply M, the joint will rotate by theta is equal to M by K. And what else happens? Each of the members, so ith member will generate a moment Ki theta, because it should be theta I, but all the theta i's are equal to theta because of compatibility. So the moment in an ith member will be nothing but Ki theta, which is nothing but Ki by K to M. So it is like if we apply M, each beam takes a moment equal to Ki by K times M. So the moment M is distributed according to the ratio of stiffnesses, right? So if I have 3 beams, this is if the stiffnesses are in the ratio 1:1:2, then the moments that if you apply a moment M, this will generate M by 4, this will generate M by 4, and this will generate M by 2. So the moment will be distributed to all the members connecting at the joint in the ratio of their stiffnesses. So what we define as distribution factor dF. So dFi is nothing but Ki by sigma Ki. So now let us look at a step-by-step procedure of how we have to use this method, the moment distribution method. So the key idea is, as usual, first identify the joints where a rotation is possible. That is, determine the degree of static kinematic indeterminacy. So procedure. The first step is to identify joints and their distribution factors. Second step, assume all the joints are locked. And compute the fixed end moments due to the applied loading. The third step is, once you have determined the fixed end moments, compute the moment imbalance. So find out the imbalance and apply equal and opposite moment. Equal and opposite moment to the joints and release them. So you compute how much the equilibrium is violated, then apply equal and opposite moments to the joints and release them. Now, once you release, what happens? We'll see what happens, right? Let us go back here. So suppose we have a joint with a far end fixed and we are applying a moment m, and if the joint is allowed to rotate by theta, since it rotates by theta, this MAB is equal to M is equal to 4 EI by L theta is generated. So if I apply M, there's M here, but what is MBA? MBA is 2 EI by L theta from the slope deflection equations plus 4 EI by L theta B, which is 0, and some term comes from the support settlement, but that is not required right now. So MBA is equal to 2 EI by L, which is M by 2. So if you apply an M here, if the joint rotates, since the beam is deforming, it generates stresses and strains everywhere, and that transmits a moment of M by 2 to the other support. So if you apply M here, when the beam is released, when the beam is not locked, that transmits a moment of M by 2 to the fixed far end. So what we should do, if we release the rotational restraint, you have to carry over M by 2. So now what do? Keep doing this iteratively. Till the moment imbalance becomes very small. It's negligible. So negligible compared to the fixed limits. So these are the steps to solve this problem. Now, just a few terminologies. If you have a fixed far end, the moment that gets transmitted to the far end when you apply an M is M by 2. So this factor 1 by 2 is called the carryover factor. Now let us take a case when the far end is hinged. And you apply a rotation M here. So the beam deforms this way. It deforms by theta. Here it has another theta B, theta A. So here, what is the carryover factor? So here the carryover factor is, any guess? Yes. Could you unmute? Okay. So if the far end is hinged, it cannot support any moment. So there is no moment that can be carried over from this end to this. So the carryover factor, if the far end is fixed, it is 0. Far end is hinged. And it is equal to 1 by 2 if the far end is fixed. That is one thing. Then what else do we have? So the same procedure can be applied to frames directly. So if you have frames with no swaying, for frames without side sway, they are very similar to continuous beams, and the same procedure can be applied directly. Directly apply the same procedure. For frames with side sway, suppose you had a frame like this, say. Suppose you had a frame like this, which is asymmetrically loaded, then how does it deform? It deforms this way. and in the process, it generates a sidesway delta. So for such frames, we need to consider the effect of this delta also on the moments that are generated. So the trick that is used is decompose it into two parts. In one case, don't allow the sidesway. One case, have the applied load and restrain this with a support so that there is no sidesway and you get all the moments that you are get all the moments generated. Plus, but this will have a support reaction here, which is not existing in the actual problem. So what you do, you find out how much is that reaction and take another problem without the applied load because we have already taken it in superposition. Now apply negative of this support reaction here. So by principle of superposition, whatever moments, internal forces, reactions that are generated in this, plus the moments, internal forces, reactions, displacement, stresses generated in this should be equal to the moments, internal forces, reactions, stresses, displacements, everything in the original problem. So we find out how much reaction is generated here and apply negative of that reaction here so that at this joint there will be zero force. So that will solve our problem of the frame with the side sway. So here you do one moment distribution and here you do another cycle of moment distribution, superimpose them. So that is the idea. Let me pause here if you have any questions. Are there any questions? Okay, I assume there are no questions. Let us quickly get into the problems for the day. Please feel free to unmute if you have any questions. So in the following figure, there are three members AO, BO, and CO connected at the joint O. All of them are equal to, all of them have the length L and EI is constant for all of them. Now they're asking us to find out the distribution factor for the member OC at the joint O. So let us do it, right? Now we should be careful because not all the joints in this are, not all of them are fixed joints, okay? So let us do it step by step in a systematic manner. What is the compatibility condition here? Can say anybody? Theta OA is equal to theta OB is equal to theta OC is equal to theta OD. Sorry, is equal to theta at O. That's it. Now what is MOC? So MOC, to determine MOC, consider this. We have O, we have C. We're applying MOC. It rotates by theta. At this point, the far end is fixed. So from the slope deflection equations, we can write MOC is equal to 4 EI by L theta O, which is nothing but theta, plus 2 EI by L theta C, that is 0, minus 6 EI by L square delta, 6 EI by L square delta. But delta is 0, theta C is 0. So it is nothing but MOC is equal to 4 EI by L theta, which means KOC is equal to 4 EI by L. So this is one result. Now let's consider the member OB. So we have O, B, and both are hinged. So how does it deform under an applied moment MOB? It deforms this way. So here it generates a theta. Here it generates some theta B. Now, if we write down the slope deflection equations for this span, we get MOB is equal to 4 EI by L theta plus 2 EI by L theta B minus 6 EI by L square delta, which is 0, and MBO is equal to 2 EI by L theta plus 4 EI by L theta B. Now, what do we know? Since the far end is fixed and there is no applied moment, MBO should be equal to 0. And if MBO is equal to 0, what does it mean? 2EI by L theta is 4EI by L theta B is equal to 0, which means when does it satisfy? For a generic EI and L, theta B is equal to minus theta by 2. Now substitute this into this equation. We get MOB is equal to 4EI by L theta, and this will become minus EI by L theta. So we'll get 3EI by L theta, which means KOB is nothing but 3EI by L. So this is the second result. Now let us look at the member OA. So let us draw the free body diagram. We have O here, A here, but A is a guided roller, something like this. We have O, we have A. Now if you apply a certain moment M here, MOA, what happens? This will maintain 90 degrees, but this will displace laterally. So we'll have something like this. So here theta A is equal to 0. So let us write it down. MOA from the slope deflection equations is equal to 4EI by L theta plus 2EI by L theta A, but theta A is 0. It remains at 90 degrees to the support, so it is 0 plus 2EI by L into 0 minus 6EI by L square delta, because this has drifted laterally by delta. So this is one equation. And what is MAO? MAO is 2EI by L theta plus 4EI by L to 0. So that is so this is 0 minus 6EI by L, 6EI by L square delta. Now what is the condition that we use? Note that there are no applied loading onto this beam except MOA, and in that case, the support reactions should be equal and opposite. But this side, there cannot be any support reaction because it is free to slide. There is no vertical restraint, which means the beam should have zero shear force. So in the absence of any applied vertical forces, the support reactions are 0. The support reaction should be equal and opposite, but the support reactions are equal to the shear force, which means the shear force is 0 everywhere in the beam. So 0 shear force. So if you draw a free body diagram of this beam, you have MOA, you have MAO. MAO is not 0. Note that the rotation is restrained, so there needs to be some moment which is taking care of it. MOA, MAO, and you have the shears V, V. So they are equal and opposite because there is no applied loading. And what is the relationship between these? So V into L, equal and opposite forces separated by L, plus MAO, plus MOA. All of them are clockwise movements. Is equal to 0, which means the shear force is nothing but minus of 1 by L times MAO plus MOA. This means that P is equal to 0. Implies MAO plus MOA is equal to 0. Now let us add these two. MAO plus MOA is nothing but 6EI by 6EI by L theta minus 12EI by L square delta. So 6EI by L theta minus 12EI by L square delta is equal to 0, which means we can eliminate delta from this equation. We get delta is equal to minus, not minus, plus theta by 2L. Now substitute this into the expression for MOA. So we get MOA is equal to what it is 4EI by L theta theta minus 6EI by L square. Sorry, this L should be in the numerator. There is an L square here, so theta L by 2. They have theta L by 2. So 4EI by L theta minus 6EI by L square into delta, which is theta L by 2. So what do we get? We get the answer as EI by L theta. Now, what does this mean? If you apply a moment equal to MOA equal to EI by L theta, this beam will rotate by theta. So the stiffness of the member OA at the point O, rotational stiffness is nothing but EI by L. So we have KOA is equal to EI by L, KOB is 3EI by L, and KOC is 4EI by L. So what is the joint stiffness? We have the joint stiffness is, so you can draw an analogy between this and springs in parallel. So this is exactly what we have if we have a rigid plate. You have K1, K2, and K3, and you apply a load P. In what proportion they'll be divided? They'll go as so in this spring, the force P1 will be K1 by K1 plus K2 plus K3. The second spring, the force P2 will be K2 by K1 plus K2 plus K3 into P. The third spring, it will be K3 by K1 plus K2 plus K3 into P. So it is exactly the same thing, only that instead of displacements, we have rotations. That is the only difference. So the equivalent stiffness in this system is nothing but K1 plus K2 plus K3. Similarly, in this system, it is KOA plus KOB plus KOC. So KOA is nothing but EI by L. KOB is what? KOB is 3EI by L. So if the far end hinged, this far end has a guided roller and far end fixed. It is well known 4EI by L. So the total stiffness of the joint is 8EI by L. Now what is asked? They're asking the distribution factor for the member OC at O. So for the member OC, it is nothing but, so the distribution factor for the member OC is nothing but KOC by K. So what is KOC? 4EI by L. And K is 8EI by L. So it is 4 by 8, which is 0.5. So the answer is in this, you can see, it's option B. Okay, I hope it's clear. Let's go to the next question. So this is a simple question. So now in question one, suppose a moment m of 2000 kilonewton meter is applied to the joint. Applied to the joint at O. What is the value of the moment MOC? What is MOC? So we have already the distribution factor OC is 0.5, which means MOC is, so this is the ratio of the total moment that is taken by a given member. That is the physical significance of the distribution factor. If you apply some total moment M, what fraction of the total moment is taken up by a given member? So that is the physical significance of the distribution factor, which means MOC is nothing but 0.5 into 2000, which is 1000 kilonewton meter. So that is option A. So I hope it is clear. From this, you can also note down that distribution factor will always be less than or equal to 1. Because if there are many members, distribution factor can never be greater than 1. So if you apply a certain moment, a member cannot take more moment than what is applied. And it has to be greater than or equal to 0 also. Because if you apply a certain moment, individual members cannot take the opposite of the moment in a general case, right? It can happen in certain complicated situations, but not when there are linear elastic beams connected at a given joint. So, and if you add all DFs, you add all the distribution factor at a joint, you should get 1 because the total moment has to be the same. So if you sum all the distribution factors, you will get 1. That you can check. You can take some example and check. Now let's go to the next question. Consider the frame given below. L is constant for all elements. EI is also constant for all the elements. What is the distribution factor for the element OA? Now we know what is the far end of OA. So OA is like this, right? OA is like this. So this is a guided roller. We found in the last problem, what is the value of KOA? Could anybody unmute and tell me what is the value of KOA? We just found. We took the slope deflection equations MOA for MOA and for MAO, and we let the shear force. We let the shear force equal to 0. And when we did that, the sum of the moments have to be 0, and we found it should be equal to EI by M. And what is KOB? Now you should be very careful, right? So as always with force methods of analysis or the displacement method of analysis, the first step is always to draw the the deformed shape. Suppose I apply a moment M and it rotates by certain theta. What will happen to the member OA? It will go like this. So it displaces by some delta. It's A, B, C, and D. So you have a roller here and it displaces, but this angle is maintained. What will happen to member OD? So this cannot displace, but it can rotate. So here it can generate a rotation like this. So this preserves 90 degrees here. So here it can have a rotation. And what happens to member OC? It develops a shape like this. So this is fixed, this is hinged. And what about this, right? So here, if I rotate this way, simply at this point, it is free to move laterally, right? And it is also free to rotate. So this just displaces laterally and generates some rotation here. So there is some rotation and also some displacement delta, which means this can remain straight. So if you apply a certain rotation, this side there is no restraint at all. So under linear elastic conditions, this remains straight. So it doesn't generate any stresses. So the moments that are generated here are zero. So in the member OB, if you see, OB is something like this. We're applying a moment, but neither the shear force nor the rotations are restrained. So it simply rotates as a rigid body like this. So under rigid body rotation, there are no internal bending moments that are generated, which means KOP is 0. Right? Why is it 0? Because the moment MOA, what is MOV? MOV is 0. There's no moment generated when the beam rotates as a rigid body. So what is KOC now? KOC is usual slope deflection equation. So it is 4EI by L. And what is KOD? KOD also we have seen in the last problem. So KOD is 3EI by L. Because OD is something like this. Applying a moment here. So it deforms this way. And we can eliminate whatever rotation is happening at D in terms of, because we have 0 moment here, you can apply that and get this. Now, what are they asking? The distribution factor for the element OA. So what is the total stiffness? The joint stiffness K is 1 plus 0 plus 4 plus 3, which is 8 EI by L. And they're asking what is the distribution factor for element OA. So distribution factor for OA is KOA by K. KOA is EI by L, this 8 EI by L, so it is 1 by 8. The correct answer is option C. Go to the next question. Now this is a different frame. So again, look at each of the members individually. They're asking to find the distribution factor for the joint O, for the beam OB at the joint O. So as usual, for OD and OB, right? They are like this. This is O, this is D or B. So this deforms this way. So we have the usual slope deflection equation. So KOD is equal to KOB is equal to 4 EI by L. EI and L are same for all the members. And what is KOA? We already solved in the first problem. So OA is something like this. If you apply a moment, it goes like this. There is a delta. We eliminate the delta by zero shear force condition. We get KOA is EI by L. And what about KOC? Any guess? So again, there is no restraint here. So if you take a free beam and you apply a rotation theta or M, whatever it is, you can apply theta without the need for any moment, right? It rotates as a rigid body. To rotate a rigid body, you don't need to apply any moment. So KOC is nothing but 0. Because this end is neither restrained in the rotation nor in translation. So it is easier, it's free to translate and it also rotates. So there is no stiffness associated with this. So what is the total joint stiffness? It is 4 plus 1 EI by L, which is 9 EI by L. And what are they asking? The distribution factor for the member OA. So it is nothing but 4 by 9. OB. So for OB, it is 4 EI by L. Total is 9 EI by L. So distribution factor is 4 by 9, which is 0.44. So that is option D. So option D. Now let's go to the next problem. So here we have an actual problem in moment distribution method. So before this, if you have any doubts, I'm happy to clarify. Are there any doubts? Okay, no problem if there are no doubts. Let me proceed. So consider this two-span continuous beam. They're asking us to find out the value of the bending moment at the point B and C. So here we'll see how the method actually works, the method of moment distribution. So as usual, now let us make a table. Okay. So, or before that, let us determine the joint stiffnesses. So we have only one joint here. The other joints are all statically, they are well known. So at the joint B, let us take at the joint, we'll start with joint A. So at joint A, how many members are connected? There's only one member. So suppose that has a stiffness K. The total stiffness of the joint is also K. So the distribution factor for the member AB at the joint A is nothing but 1. Let's see joint B. So for the joint B, there are two members connected there. So let us say KBA. What is KBA? We see that the far end of the member AB at the joint is hinged. So it generates 0 moment under an applied rotation. So KBA is, we have already solved in the previous examples. It is 3 EI by L. So KBA is 3 EI by L. And what about KBC? For the span BC, the far end is fixed. So from the slope deflection equations, we get it is 4 EI by L. So what is the total joint stiffness? It is 7 EI by, sorry, this is K by L, LAB. The lengths are not the same, and here it is LBC. So let us substitute the values. We get 3 EI by LAB is 6 plus KBC is 4 EI by LBC is 8. So the total stiffness is this is 0.5 plus 0.5, which is EI. So the joint stiffness is EI, and KB is nothing but 0.5 EI. KBC is nothing but 0.5 EI. So the distribution factors corresponding to the spans BA and BC is 0.5. So if you apply a moment at the joint B, half of it will go to the span AB, and the other half will go to the span BC. And for joint C, we don't need to worry, because any moment that is applied is directly taken by the fixed end. It can support any moment without undergoing any rotation. So this is done. You have determined the distribution factors. So this is basically step 1. What is the next step? The next step is to log all the rotations and determine the fixed end moments. So step 2. Determine the fixed end moments. Assuming that all the rotations are frozen. So the joints are not allowed to rotate, which means everywhere the slope is 0. I mean, at every joint, the slope is 0. So each span behaves as a fixed beam. So you can compute the fixed end moments due to the applied loading. So if you see span AB, after locking all the rotations, you have something like this. You have W and span L. You can use the conjugate beam method to determine what will be the support moments that are generated. Since this loading and the geometry is symmetric about the middle plane, you can say the moments that are generated will be equal. So by the conjugate beam method, you can say that due to the applied loading, you have a certain moment. If there was no fixed moment, you have, what is this? This is WL squared by 8. And due to the fixed end moments, you have another loading on the conjugate beam, which is like this. Suppose this is M. And we know that fixed end has to be replaced by a free end, which means this beam has to be in equilibrium without the need for any shear forces. So the total vertical force should be equal to the total horizontal force. And since the loading is symmetric, the point of action of both the forces is through the center. So there is no net moment that is generated. So the shear force is 0, which means what's the area of the parallelogram? It is M by EI into L is equal to area of the parallelogram is 2/3 of WL square by 8 EI into L. So you get M is equal to WL square by 12. So the fixed end moment due to an applied distributed loading is WL square by 12. And same operation you can repeat for a point load. So you have a point load in the other span, say call it BC. So here, which means here you have WL square by 12. Hogging moments. Here also you have some moments M. And because of symmetry, these two should be equal. So again, use the conjugate beam method. Due to the applied loading, you have something like this. And due to the fixed end moments that are generated, you have something like this. So in the absence of shear force, in the absence of any support reaction, the shear forces have to be 0 and the moments at the ends have to be 0. So since the loading is symmetric, there is no net moment that is generated. So the total force has to be 0. The total downward force is M by ML by EI, and the total upward force is PL by 4 into L by 2 by EI. So you get M is equal to PL by 8. in this case. So what are the fixed end moments that we have with the correct sign convention? You note that here the moment is counterclockwise. So MABF, fixed end moment at A in the span AB is minus WL square by 12. And W is how much? It is 16, L is 6. So we have minus 16 into 6 square by 12. It's nothing but minus 48 kilonewton meter. And what is MBAF? MBAF is plus 48 kilonewton meter. It's in the other direction. So what about MBCF? MBCF is PL by 8. P is almost 24 kilonewtons. So it is 24 into, again, it is hogging. Sorry, it's counterclockwise. So 24 into 8 by 8, which is minus 24 kilonewton meter. And MCBF is 24 kilonewtons meter. Note that MBAF plus MBCF is not equal to 0. So if you add these two, you're getting 48 minus 24, which is 24. So there is an unbalanced moment of 24 kilonewtons meter at the joint B. So now let us get into the moment distribution iterations. So let us make a table. So let me call the first column as description as to what is happening there. Description. And then what are the joints? We have joint A, we have joint B, we have, so this is the span AB. So in span AB, you have these two. And in span BC also you have these two joints, B and C. So we have already determined the distribution factors. So A is a hinge joint and there's only one member connected there. So it is 1. What about B? For B, we saw that the distribution factors are equal. So it is 0.5, 0.5. And at the joint C is a fixed joint. So you really don't need to worry about the distribution. Now, what is the next thing that we need to look at? It's the fixed end moment. Fixed end moment, 8 kilonewtons meter. We saw that MABF is minus 48. Here you have minus 48 kilonewton meter. Here you have plus 48. Here you have minus 24. Here you have 24. This is based on the assumption that all the joints are frozen. They are restrained from rotating freely. So if they are restrained from rotating, you generate so much. But this system of moments is not in equilibrium. So here you have an unbalanced moment of 24 kilonewton meter. So you allow rotation. So here you have this step, allow the rotation. So once you allow rotation under an action of a counter moment. So there is an unbalanced moment of 24 kilonewtons meter. Let us apply a counter moment of minus 24 kilonewtons meter at the joint B. And at joint A, at a joint A also the moment has to be 0 because it's a hinge joint. So here let us apply a counter moment of 48. Now, how are these counter moments distributed to the different members according to the distribution factor? So here there's only one member. So let me put a box so that it means we shouldn't sum them up in the end. So 48 comes to the member AB. From here, minus 24, half of it comes here. So minus 12 comes to the span BA and minus 12 comes to the span BC. And here we don't need to distribute the moment because it's a fixed end. It can take any amount of moment without undergoing rotations. But here the moment has to be 0. Now, once you allow rotation, because of the rotation, the beam is undergoing deformation. It gets stressed and it transmits a certain fraction of the moment to the other end. How much is that? So this is the carryover moment. So some moment gets carried over from A to B. How much gets carried over? It is m by 2. So the far end is kind of fixed here. So 24 gets carried over here. Will anything get carried over from here to here? No, because this is a free end, this is a hinged end. So the carryover moment is 0. Similarly, in the span BC, due to the rotation of the joint B, a certain amount of moment gets carried over to the fixed end, which is -6, half of it. So once it is carried over, now you can look at the joint B. So because of the carryover moment, you have an unbalanced moment of 24 kilonewtons in the joint B. So this is an unbalanced moment at joint B. So again apply -24. So apply -24 here. So part of it, how much goes here? Again, it is -12. -12. Let us see. Yeah, so -12, -12. And then here it is 0. So there's nothing coming from here. And here also it is 0. Will anything will anything get carried over from here to here? No, because this is a hinged end. So allow rotation. Can carry over. So here you have 0. So nothing gets carried over. So here also nothing gets carried over. So it remains 0. But here it gets carried over. So here you're allowing rotation. So from here you get -6 again. And from the fixed end, nothing gets carried over here. So here it is 0. So here it is 0. So here actually 0/2, which is 0, gets carried over. From here, nothing can get carried over because the carryover factor for far end hinged is 0. Here again, the fixed end cannot transmit anything to other side, but here from here it goes to the fixed end. Now this is the end of the iterations because all the carryover moments are 0 at this stage, and there is no unbalanced moment at the joint B. So let us compute the total moment after all the distribution is done. So let us compute the total moment here. Total moment in kilonewtons meter. It is, so here it is -48 plus 48, which is 0. And that is consistent with the fact that it is a hinged end. It cannot have any non-zero moment. What about the moment at MBA? We have 48 -12 plus 24. So these three get cancelled and we get just 48. Here, what do we have? -24, -12, -12, which is -48. Now note that MBA plus MBC is equal to 0. So equilibrium is satisfied in this case. And what is the moment at the joint C? You have 24 -6 -6, which is 12 kilonewtons, meters. So what is the bending moment diagram like? You have something like here it is 0. And here it is a hogging moment of 45. So in between it is sagging because the load is downwards. Here it is something like this. So at joint B you have -48. Note when you draw the bending moment diagram, you need to take the signs according to sagging or hogging. But when you solve for the when you use in the displacement method, you need to take the signs according to clockwise is possible. And in the other span, the moment is 12, which is hogging. So again, in the other span also calculate this. So here it is 12 kilometers hogging. So MB is equal to this and MC is equal to this. These values you can compute by superposition as an exercise. These things you can take care. So which option does it correspond to? MB is 48. So they're only asking the absolute value, so you don't need to worry about the minus sign. MB is 48 and MC is 12 kilonewton meter. So the correct answer is option A. Is there any doubt? Yes, I'm not able to hear you. Are you? Is there any doubt? Could you? Okay, it looks like it's clear. Let's go to the next. Yes. Yes, Naganathan, is there any doubt?
No, sir. No, sir.
Okay, thank you. Let me mute your mic because there's some disturbance.
Thank you.
The next question is to compute the reaction at the point B due to the applied loadings. So that is very simple. We already have MABF. So it is very simple. You just draw the free body diagram. So here the moment is 0. There is so let us call this VAB, VBA, and at the joint we have VBA, VBC, and reaction at B. And for the span BC, you have VBC, VCB. Let us only consider the forces. So we have an applied loading and we have MAB, MBA. Here you have MBC, MCB. And you also have this applied loading of P. Let us, for the span AB, let us take moments about the point A. So if we take moments about the point A, what is the equation we get? Let us take clockwise moments as positive. So plus VBA into L plus MBA plus MAB plus WL into acting at L by 2. So WL square by 2 is equal to 0. So VBA is nothing but WL by 2 minus WL by 2 minus MAB plus MBA by L. So W is 16. L is 6. So 16 into 6 by 2 is 16 3s are 48. So we have minus 48 kilonewton meter. Minus what is MAB? MAB is 0 because it's a hinged support, and MBA is 48. We determined it is 48 kilonewton meter clockwise. So it is minus 48 by L. So L is 6. So 48 by 6 is 8 kilonewton. So VBA is nothing but minus 56 kilonewton meter. Sorry, not meters. They have already divided by minus 56 kilonewtons. And then let us look at span BC. The span BC, again, let us take moments about the, because we need VBC, we can take moments about the point C. So if we take moments about the point C, VBC into L minus P into L by 2 plus MBC plus MC is equal to 0. So this means VBC is equal to PL by 2 minus, so not PL by 2, it is P by 2. P by 2 minus 1 by L MBC plus MCB. What is MBC? MBA is plus 48 kilonewtons. So MBC is minus 48. And what is MCB? MCB was, I guess, MCB is minus 12. Sorry, MCB is plus 12. So MCB is plus 12. and the length is 8 meters. P is 24, so 24 by 2 is 6. So this is 36 by 2, 36 by 8. So 36 by 8 is 4.5. And just a minute. How much is P? So P is P is 24, not 12. So it is. So this is 24 by 2. It is 12 minus 36 by 8. So 36 by 4 is 9, and 4 by 2, 9 by 2 is minus 4.5. It is 16.5 kilonewtons. Now, if you take the free body diagram of the joint P, we get RB is equal to, so the total, the downward net upward force is equal to net downward force. Net downward force is VBC minus VBA. VBC minus VBA. VBC 16.5 minus 56, which is 72.5 kilonewtons. So the reaction at the support B is 72.5 kilonewtons. Since it is positive, the assumed direction is correct, so it is upwards. So the correct answer is option C, 72.5 kilonewtons upwards. Okay, now let us go to the next question. Consider this other beam. What is the fixed end moment at beam for the beam BC? And what is the moment distribution factor for BA at the joint B? So again, this is very simple. Both the far ends are fixed. So KBA is 4 EI by L. In this case, L is 4 meters, so it is nothing but EI. KBC is 4 EI by L, which is L is 6 meters, so it is 2 by 3 EI. So distribution factor. So what is the total joint stiffness? The total joint stiffness is EI by L plus 2 by 3 EI, which is 5 EI by 3. So distribution factor for BA is nothing but EI by 5 EI by 3, which is 3 by 5, 0.6. And the distribution factor for BC is 2 by 3 by 5 by 3, which is 2 by 5, which is 0.4. What else is asked? They're asking the fixed end moments at the joint B. So let us determine the fixed end moments. What is, we have already derived the formula. So MABF is minus WL square by 12. In this case, it is minus 3 into 4 square by 12, which is minus 4 kilonewtons meter. MBAF is just the negative of this, so 4 kilonewtons meter. What is MBCF? MBCF is minus 5 into 6 square by 6, which is by 12, which is 36 minus 15 kilonewton meter. And MCBF is 15 kilonewtons meter. Now they're asking the fixed end moment in BC and the distribution factor for BA. So you can see that it corresponds to option B. So this is simple. The next step is to do the moment distribution systematically. So they're asking to determine the bending moment at a certain joint. So that can be determined only when we do the moment distribution process. So as usual, let us make the table. We have the description. So in span A, we have the joints A, B, and in span BC, we have joints D and C. We have already got the distribution factors. So at A, it doesn't matter, it's a fixed end. It can take any amount of moment without rotating. At B, we have this is 0.6, this is 0.4. I hope it's correct. MBA is, sorry, DFBA is 0.6 and 0.4. Let's see, it doesn't matter. And the fixed end moments, MFR. At A, what did we get? We got -4. At B, we had +4. Here it is -50. Here it is 50. Now, what is the first step? So iteratively, we are going to do it. So this is already frozen. Now this is already frozen. Now allow rotation. So how much rotation we should allow? So what is the unbalanced moment here? It is -11. So you need to supply opposite of it, which is 11 kilonewtons meter. So again, I'm boxing it just to indicate that this should not be added up in the final thing. So in what fraction we should distribute? So 0.6 and 0.4. So 0.6 of 11 is 6.6. 0.4 is 4.4. Now, once you allow rotation, since the beam is trailing, it will transmit a half of the moment to the fixed end. So do the carryover operation. 6.6, you get 3.3 here. And from 4.4, you get 2.2 here. Now what happens? So, so at this joint, we have from here, there is no carryover because it's a fixed end and this is also a fixed end. You cannot get, nothing gets carried over because the fixed end doesn't rotate. So this is the end of the iterations. So what is the net moment at the joint A? We get it as -4 plus 3.3. It is total moment in kilonewtons meter is -0.7. At the joint B, it is 4 plus 6.6, which is 10.6 kilonewton meter. And here it is -15 plus 4.4. So it is 15 minus 4.4 is 10.6. So there's with a negative sign. Note that the joint B is in equilibrium. There is equal and opposite moments in the two spans connected to the joint B. And here we have 17.2. So what is the moment at the joint B? So the moment at the joint B, total moment at the joint B is 10.6 kilonewtons hogging. Put a -6. So on the right end, if you have a clockwise moment, it means it's hogging. That is well known. So the answer is option A. So I can pause here if there's any doubt. Okay, if there are no doubts, I'll proceed. So the next problem is a bit lengthy because it is a sway frame. We need to do it in 2 steps with 2 moment distributions. Let's do it. So consider this frame. So easily you can say that because of, so it is symmetric, the geometry is symmetric, the vertical load is symmetric, but you have an unsymmetric horizontal load. So definitely the portal frame is going to have a side sway. And in the presence of a side sway, as I already said, we have to split this problem into 2 parts. So one moment distribution where the side sway is restrained by a support. So this is one problem. And the other problem is we actually don't have a support. So whatever reaction is generated at the support in problem 1, apply negative of that reaction here and solve for the unknowns. That's it. So from here you have one moment distribution cycle. From here you have one moment distribution cycle. Finally, superpose both the results. That is what we are going to do. Now, Let us consider, so as usual, the first step is to determine the distribution factors. So for span, let us consider joint B. The far end is fixed at for the span BA. So KBA is 4 pi by L. What is 4? L? L is 20 meters, so it is 0.2. 4 by 20 is 1 by 5, so it is 0.2 EI. What is KBC? So in the initial step, when you restrain the rotations, so KBC is 2 EI by 4 EI by L again. But L is different, so it is 4 by 24, 1 by 6, so it is 0.16667 EI. So the total joint stiffness is 0.36667 EI. And the distribution factors, if you compute, they turn out to be 0.2 by 0.3667 is 0.545. So you'll get 0.54 bar. Let me truncate with 3 digits of decimal. And the distribution factor for the span, it's not AB, it is BA. BC is 0.455. So you can see that the structure is symmetric, only the loading is unsymmetric. So for joint C, it is almost the same as joint B. Only thing is you get distribution factor for joint for CB. So CB is the same as BC. So you get this to be equal to 0.455. And the distribution factor for CD is 0.545. The next step is to determine the fixed end moments. So first, let us consider the structure 1. For structure 1, the fixed end moments are as follows. What is MABF? There is no loading in the span AB, so the fixed end moment in this joint is 0. What is MBAF? MBAF is also 0. MBCF is, as usual, minus WL squared by 12. So it is minus 1.5 into L is 24 square by 12, which is minus 72 kilonewton meter. And MCBF is 72 kilonewtons meter. And what about MCDF? Is MDCF is 0 because that span also supports no transverse loads. This 15 kilonewtons is a horizontal load, but since that is applied at the joint, that will not cause any fixed end moment. So it's like applying a load at the fixed support. So the entire load will be taken just by the support. The moment arm is 0, so there will be no fixed end moment due to a load applied at the support. So these are the fixed end moments. Now let's get started with the moment distribution. So description. So here we have joints A, B. This is in span KB. B, C, C, and then D. So the distribution factors are as follows. We have A doesn't matter, it's a fixed end. Here it is 0.545. Here it is 0.455. Here it is 0.455. 0.545. And here it doesn't matter. What is the next step? Fixed end moments. So MF. Here it is 0, 0. Here it is minus 72, 72. Here it is 0, 0. Now what is the next step? Allow rotation. So allow rotation under the counter moment. So here the net imbalance is minus 72. So you apply a counter moment of 72 here. You apply, so in what fraction you should split them? So 72 into 0.545 will come to this span, and 0.455 into 72 will give to this span. So the numbers are like this. Done the calculation before. So So here we get 39.24. Here you get 32.76. At the joint C, the net imbalance is 72. So here we need to apply a counter moment of minus 72 kN. When you apply them, you have the same fraction. So here it is 39.22. Here it is with a negative sign, minus 32.76. So since you have allowed a rotation, there will be a carryover moment to the supply. So half of it will get carried over here. Half of this will get carried over here. Not only that, half of this will get carried over here and half of this will get carried over. Because these joints were also assumed to be fixed relative to each other. So half of this is 19.62. Half of this is minus 19.62. Just a minute. Half of 32.76 is minus 16.38, and this transmits 16.3. Now again, look at the joint B. You have an unbalanced moment of 16.38 here. So apply a counter moment of 16.38. Here you need to apply a counter moment of minus 16.38. So again, assume it is fixed. Now allow a rotation. What will happen? This has to be distributed. This counter moment has to be distributed to the two spans connected at joint P. So you get 0.545 into 16.38, which is 8.927. 8.927 here and 7.453 to this span. So here it is just the negative of it, minus 7.453 and minus 8.927. Again, because of the rotation, there will be a carryover to the far end in each case. So this carried over moment of 4.464. Here you have minus 4.464. So again, half of this is 3 minus 3.726. Here you have plus 3.726. So you can see that the imbalance in the joint moment is reducing from 72 to it's only 3.726 in this case. So it is drastically reducing. So once it reduces to a very small value, such that it doesn't affect engineering, it's a very small value for engineering applications, then you can stop these iterations. So in successive steps, this will reduce very much, as you can see. So this is a fixed end moment that is generated. So if you fix it, so much moment will be transmitted. But now we are not going to fix it. We have to allow rotation. So apply a counter moment. So how much is the counter moment here? You need to apply 3 plus 3.726. And here we need to apply minus 3.726. So split it in the same fraction. So 0.545 into 3.726 is 2.031 and 1. This is 0.455 into 3.726 is 1.66. Similarly, minus 3.726 into 0.545 is minus 2.031 and minus 1.696. Now carry over the rest. So from here to here, here to here, here to here, here to here. So half of this is 1.016. Here it is minus 1.016. Half of this is minus 0.848. Here it is plus 0.84. You can easily see that the unbalance in the applied moment has reduced from 72 to 0.848. So that is nearly just 1% of the initial, almost 1%. So it is also divided. So this is a good place to stop the iterations. So let us apply a counter moment of, so counter moment of 0.848 here and a counter moment of minus 0.848. So this has to be split according to the 0.545 and 0.455. So you do, so here you get 0.462 and 0.386. So here it is minus 0.386 and 0.386. So here there's an important point to note that you have to stop the iterations before carrying over the moment to the fixed. So this is what is obtained by applying a counter moment, and this will be satisfying the equilibrium. So we are applying a counter moment just to satisfy the equilibrium. Once you carry it over to the supports, that there will be a net unbalance. So since we want to satisfy equilibrium, we can stop the iterations right here. So apply counter moment. And since this value is very small compared to the fixed end moments, you can stop right here. If you carry it over, then equilibrium will be violated. So stop right here. And compute the total moments. So add them all up. 0 plus 19.62 plus 4.464 plus 1.06. So these two you get 4.48. 4.48 plus 19.62 is just so 0.62 plus 0.48 is 0.1, 1.1. 19 plus 4 is 24, 25. So 25.1. And here you can add them all up. So 39.24 plus 8.927 plus 2.031 plus 0.46. It turns out to be 50.66. Here you have minus 72 plus 32.76, which is nothing but 39.24. Minus 16.38 plus 7.453, that is 8.927. Minus 3.726 plus this. So keep adding all these. You have to add minus 72, 32.76, minus 16.38, 7.2453, minus 3.726, plus 1.696, minus 0.848, plus 0.386. Add them all up, you get the total moment exactly minus 50.6. So note that equilibrium is satisfied here and there is no unbalance. There is an unbalanced moment, but the unbalance is very small. 0.462 plus 0.38 is of the order of 0.7, which is less than 1% of the initial unbalance. So I can stop it here. So similarly here it is minus 50.66, 50.66. Sorry. So this is precisely the negative of this. So you get a positive sign here. Here you get negative of this. Here you get minus 20. So these are the final moments that we get for this structure, this portal frame structure. So MA, this is MA. MB, you take the positive sign convention, it is minus 50.66 again. MC is $50.66. The minus 50.66 again. And MD is 25.1, which is sagging. So So now let us compute what should be the reaction force on. So this is the structure that we are solving, right? Note that the force 15 kilonewton did not enter our moment distribution at all. So now let us solve this structure. So we have this structure. We have NA is sagging 25.1. We have a horizontal force here. We have vertical loading here. We have an unknown horizontal. So this is 15 kilonewtons. Here we have an unknown reaction force R. Here we have W. Here we have again sagging 25.1. And also we have these support reactions. Right? We have these support reactions, which are unknown right now. So to determine them, let us take the member CD. So take member CD. So in the member CD, we have this. So this is D, this is C. There is a certain shear force. There are no intermediate forces. There are no span loadings. So we have a certain shear force like this. So let us take this as MDC, MCD, VB, and on the joint C, you have V acting like this, VCD. And you have the force from. So the axial force does not change. So from this side, you have VAB. Okay, so and on the joint, you also have R, which is the unknown reaction force. So let us determine this. So what is VCD? VCD is nothing but minus of MDC plus MCD by L. What is L? L is 20. So minus MDC plus MCD is MDC is minus 50.66. MDC is minus 25.1. MCD is minus 50.66. So it is so the answer is 3.78 kilonewtons. That is fine. And in what about AB? So similarly, VAB, to take it this way. So you have VAB plus the applied force. So VAB is nothing but minus MAB plus MBA by L. So it is nothing but minus 25.1 plus 50.66 by 20, which is nothing but minus 3.78 kilonewtons. So there is already a shear force in the right hand side in towards the right in the at this point in as minus 3.78, plus there is also a force 15 kilonewtons that is acting. So the net force coming on to this point in this beam. So this beam is compressed on both sides by a force of 15 plus VAB, which is 15 minus 3.78. So the force is 15 minus 3.78, which is 11.22 kilonewtons. So VAB plus 15 is equal to 11.22 kilonewtons. And what is R? If you establish equilibrium for the joint C, so sigma fx equal to 0 at joint C. If you do that, you get VAB plus 15 minus VCD is equal to R, which means VAB plus 15, we already got it as 11.22. So 11.22 minus 3.78 is equal to R. So R is equal to 15 kilonewtons. So this is the value of R. And which option does it correspond to? R is equal to 15 kilonewtons. This is option A. So I hope it is clear. Let's go to the next part of the question. Now we have determined if it is a non-sway frame, we need a reaction force of 15 kilonewtons from the other side to stop it from swaying. But it is a sway frame. That is the thing. So, but it is a sway frame. So let us consider problem 2. What was problem 2? You take the frame, right? You take the frame and apply R here. But we don't know for a given, suppose, so this is what we need to do so that there is no net reaction here. But before we solve the problem, we don't know what will be the sidesway here. So the trick in linear elasticity is to use superposition. So suppose you take this frame and apply a sidesway of suppose you apply a sidesway of delta, it will require a certain reaction R of delta. Let us call that as some R prime, right? So, or rather, if you apply in a more precise terminology, I can say you're applying a force here and you're measuring the displacement here. So this point you will have the force that needs to be applied is K1 and K11 into delta, where this is the point 1. So K11 is the stiffness coefficient that relates the displacement of the point 1 to the force applied at point 1. So if K11 is the stiffness coefficient, you need to apply K11 delta to cause the displacement delta. So that is what it means. But we don't know what is the delta beforehand. We want K11. We want K11 delta to be equal to R, right? But we don't know what how much delta we need to apply. So let us start with a guess. So let us say, let us simply take delta as just a minute. So let us start with a guess. Let us take delta to be equal to. So this is not the actual delta. Let us put some delta cap. So let us say delta cap is equal to 500 by EA. Or rather 5000 by EA. Right? This is just a realistic value. So let us take delta cap as 5000 by EI and see what is the answer that we get. Okay. So as usual, what is the first step? Step 1 is to determine the distribution factors, but that is already done. Step 2 is to determine the fixed end moments. Fixed end moments. To determine the fixed end moments, what do? We assume that the joints are restrained from rotating. So we need to understand very carefully. Here you have a rotation of theta B and theta C, the joints. So here you have a rotation of theta B and theta C at the joints. But when you want to determine the fixed end moments, The structure, the deformed shape that you take is something like this. You're not allowing these joints to rotate. So the deformed shape is something like this. And this delta cap is nothing but 5000 by E. So let us find the fixed end moments. Right? So for now, this is delta cap. If this member is axially inextensible, this is also delta cap. And what are the moments that are generated? Let us find them out. So let us consider span AB. So span AB is something like this. This is A, this is B. You have a delta cap. And what is the moment that is generated here? MABF, MBAF. There is no rotation. So by the slope deflection equations, MABF is equal to 6 minus 6 CI by L square delta cap. But what is delta cap? It is 5000 by EI. So EI gets cancelled. You get delta cap as 5, 6, 30. So minus 30,000 by L square. L is what? 200. Sorry, 20. 20 square. So this turns out to be. Let me check. Something is. Anyway, it doesn't matter actually. So we do one thing. Okay, so no problem. Everything is fine. So this turns out to be 75 minus 75 kilonewton meters. And MBAF is what? That is also equal to minus 6 CI by L square delta cap, which is minus 75 kilonewton meter. So now you know why I have taken 5000, just to get realistic values of the moment. Otherwise, you may have to deal with very small moment values. So delta cat can be any arbitrary value, but if you take it this way, you get some realistic values for these moments. That's all. We don't want to deal with very small or very big values. That is the only reason. Similarly, what is MBC? So MBC, you see that the theta B is 0, theta C is 0, and there is no chord rotation. So MBCF is 0, MCBF is 0, and MCDF is the same as MBAF, which is minus 75 kilonewtons meter. And MDCF is also the same. Now let us do the moment distribution. So we have description. Distribution factor. We have the joint A, joint B, B, C, C, D. So the distribution factors are the same. At the joint B, we have 0.545, 0.455. Here you have 0.455. Here you have 0.54. Minus the fixed end moments, kilonewtons meter are minus 75, minus 75, 0, 0, minus 75, minus 75. So these are the fixed end moments. What is the next step? You need to allow a rotation. So how much rotation? You need to apply so much rotation as to get a counter moment of 75 at this joint. Value 75 at this joint as well. In what fraction you should split them? Split them as 0.545 and 0.455. So if you do that, you get the numbers here. So it is so here you get 40.875. For here it is 34.125. And then here it is 34.125 and 40.875. So this is after allowing each. But if it rotates, there is also a carryover moment of half the values. So the carryover moment is nothing but 40.875 by 2, which is 20.4375. And here you get 34.125 by 2. So here it is 17.0625, 17.0625. Here it is 20.4375. Now you have an unbalanced moment of 17.0625. So apply minus 17.0625 here. Similarly, here also you apply minus 17.0625. Again, allow rotation. So when you do that, you need to distribute it. So what is the value? You get here it is minus 9.299. Here it is minus 7.7635. Here it is again minus 7.7635, minus 9.299. Now carry over half of this, half of this, half of this, half of this. So here you get minus 4.6495, minus 4.6495. And half of this one is 7.7635 by 2 is 3.88 minus 3.888 minus 3.88. Now you have an unbalanced moment of minus 3.8818. So you apply plus 3.8818. Here also 3.8818. When you apply that, again you allow rotation, split them up. So here you get 2.1155. And here you get 1.737. So here it is 1.737 and 2.1155. Again, do the carryover operation. So if you do that, you get 2.1155 by 2, which is 1.0578, 0.0578, and half of this gets go here. 0.737. 0.8685, 0.8685. So again, this is a right place to stop because you can see that 0.86 is very small compared to the initial unbalanced moment of 75. So we can stop the iterations here. So you just split this minus 0.8685 into two parts. So what they are, here you get a minus 0. So here you're applying minus 0.8685. So here you get minus 0.4735 and minus 0.39. Also it is minus 0.395, minus 0.37. And here you stop. Do not carry over. Find out the total forces. What is the total? Total moment is 100 and so add them all up, minus 75 plus 20 minus 4 plus 1, you get something like minus 58.59. So this is also the same, minus 58. And in between it is here minus 75 plus 40 minus 9 plus 2 minus 0.4. That turns out to be minus 41.782. So this is also minus 41.782. This, if you add up, you'll get 41.75 to 41.75. So note there is a slight discrepancy, the second digit, but that is still okay. So the moment imbalance is very small in this case. So it is 0.78 minus 0.75. It is like 0.03 in 75. So that is a very small discrepancy. So this is a good place to stop. Now here comes the main step. So what we have is delta cap, and we can determine K11 delta cap. So what is K11 delta cap? So which is nothing but the force that needs to be applied here. What is the force that needs to be applied there? That we have to see. So since the structure is symmetric, let us consider the full structure at once. We have this. We have an applied force here. Of R. We have K11 delta cap is applied. And we'll see how much this is. So the moments are like this. Here it is a sagging moment. Here also it is. Here it's sagging moment. So as usual, let us find out VAB is nothing but so at the joint. So if you draw the free body diagram, you have something like this. For this, you have something like this. VAB, VAB, VCD, VCD. And at the joint C, you have VAB, VCD, and the reaction, not reaction, this K11 delta. So let us determine VAB as MAB plus MBA by L minus of that. So what it is? Minus 58.59 minus 41.78 divided by L is 20. This minus 5.10, 5. Minus 5 minus 5.0185 kilometers. VCD is also the same because it's the same two numbers. So we have minus already, so it is plus. So plus. Just a minute. Yeah. Let us see. VCD is that is fine. VCD is also 5.085 kilometers. Now establish the equilibrium of the whole structure. So you see VAB is in this direction. So you have K11 delta cap. You have VAB and VCD like this. There are no other horizontal forces in the structure, which means K11 delta cap is nothing but sum of which is $10.037. But we don't want delta cap. What we want is delta. So we have this relation K11 delta is equal to 15 kilonewtons and K11 delta cap is equal to 10.037 kilonewtons. Which means delta by delta cap is equal to 15 by 10.037. And delta cap, we have already chosen it as 5000 by AI. So delta is equal to 15 by 10.037 into 5000 by AI. So we'll find what this is. So 15 by 10.037. So this is something like 7472.35 by EI. So this now what do we need to do? So when we had actually we don't need this number. So we don't need to find delta. So for superposition, we need, so if we have say MA, the moment at A is nothing but moment at A in problem 1 plus the moment at A in problem 2. In problem 2, we are expected to apply a load of equal to the reaction, which is 15, which means it is M at A of problem 1 plus M at A in problem 2 when delta is equal to some when R is when the reaction is equal to 15. But in our case, the reaction is only 10.037, right? So which means since it is a linear elastic problem, it is nothing but MA in problem 1 plus MA in problem 2. If we find it for R equal to 10.037, multiply that by 15 by 10.037. That is what it means. Because the reaction scale linearly with the delta, which means if we are instead of delta cap, if I apply delta, we get this. And the ratio of delta by delta cap is this, which is equal to 1.4944. So what we need to do is the moment at A is nothing but a superposition of the moment at A in problem 1 plus 1.4945 times the moment at A in problem 2. So what are the values in problem 1? I think it is 25.1. It is in problem 1 is in the previous page. Yeah, 25.1. And in problem 2, it is 58.59. So it is. Just a minute. So plus minus 58.59 into 1.4945. So this turns out to be minus 62.46 kilonewtons meter. So the moment at A is minus 62.46 kilonewtons meter. If you see which option it is option B, 62 kilonewtons meter. They're only asking the absolute values. So that brings us to the end of today's session. Can ask me if there are any questions. I'll wait for a few minutes. If there are none, I will close the session. Okay, it looks like there are no questions. So thank you all for attending the session. I hope it is helpful for you to solve this week's assignments. We'll meet next week at the same. Thank you.